Dear students, இந்த வீடியோவில் நம்ம chemical kinetics இந்த lesson இரண்டாவது பகுதி பார்க்க போகிறோம். ஸோ முதல் பகுதி chemical kinetics lesson உடைய முதல் வீடியோ பதிவில் நம்ம என்ன பார்த்துருந்தோம், கைனெட்டிக்ஸ்னால் என்ன, அதனுடைய applications of kinetics, rate, order, rate law, rate equation, molecularity. ஸோ இந்த டாபிக்ஸ்லாம் நம்ம டிஸ்கஸ் பண்ணியிருந்தோம். இந்த வீடியோ பதிவில் நம்ம இரண்டாவது பகுதியை பார்க்க போகிறோம், கெமிக்கல் கைனெட்டிக்ஸ் பார்ட் 2. ஸோ இந்த டாபிக்ஸ் எல்லாம் நம்ம இந்த வீடியோவில் நம்ம பார்க்க போகிறோம். ஃபஸ்ட் ஆர்டர் ரியாக்ஷன், இன்டெகிரேட்டட் ரேட் லா ஃபார் ஃபஸ்ட் ஆர்டர் ரியாக்ஷன், graphical representation of first order reaction, half-life period of first order reaction, examples of first order reaction. இதே போல் zero order reaction, integrated rate law for zero order reaction, graphical representation of zero order reaction, half-life period of zero order reaction, examples of zero order reaction. Then factors affecting the reaction rate, pseudo first order reaction, rate determining step. So இந்த டாபிக்ஸ் இந்த வீடியோவில் நம்ம பதிவிட போகிறேன், சரியா? ஸோ நல்லா கவனமாக கேளுங்க, திரும்ப திரும்ப இந்த வீடியோ பதிவை பாருங்கள். ஸோ யூ வில் கெட் கிளாரிட்டி இன் தி கான்செப்ட். ஃபர்ஸ்ட் வில் டிஸ்கஸ் அபவுட் ஃபஸ்ட் ஆர்டர் ரியாக்ஷன், இன்டெகிரேட்டட் ரேட் ஈக்குவேஷன் ஃபார் ஃபஸ்ட் ஆர்டர் ரியாக்ஷன். இது ஒரு டெரிவேஷன். வாட் இஸ் ஃபஸ்ட் ஆர்டர் ரியாக்ஷன்? Rate depends on first power of the concentration of the reactant. That is, rate of the reaction depends only on the any one reactant. Such reaction is called first order reaction. So how to get rate constant for the first order reaction? Say now let us consider A gives product is a first order reaction. So what is the meaning? The rate of the reaction is directly proportional to concentration of only one reactant. That's called first order reaction. Consider the reaction A gives product. At time t is equal to 0, the concentration of reactant is A0. After some time t, the concentration of the reactant remaining left as A. So you remember, A gives product is a first order reaction because the rate of the reaction depends only on the first power of the concentration term, only one reactant. At time t is equal to 0, concentration of reactant A is A0. After some time t, the concentration of the reactant left remaining is A. Now we know the rate. Rate is equal to K into A power 1. So it's a first order reaction. We know that rate is change in concentration of the reactant in unit time minus dA by dt is equal to Ka, and you can rewrite this equation. Concentrations are in one side, constant in another side. So in the dA, in the A in the side kondu vaanga, minus dA by A is equal to K dt. Integrate this equation on both the sides with the limits of t to t equal to 0 to t equal to t with the concentration of A0 to A. So now integrate this previous equation with the limits of A0 to A, integration A0 to A dA by A is equal to K into integration t is equal to 0 to t equal to t dt. If you integrate, you will get minus ln A power A by A0 is equal to Kt to the power t by T0. Now you substitute the limits, upper limits minus lower limits. Minus ln A minus of minus ln A0 is equal to Kt into t minus 0. So you can rewrite minus into minus plus ln A0 is equal to ln A is equal to Kt. You know well, log A minus log B is equal to log A by B. Based on that formula, you rewrite this equation ln A0 by A is equal to Kt. You can rewrite K is equal to 1 by T ln A0 by A. This is a rate constant for first order reaction. You can convert the ln into log. You know very well, ln is equal to 2.303 log to the base 10. So you can rewrite K is equal to 2.303 by T log of A0 by A. This is called rate constant of first order reaction, where T is the time taken. A0 is the initial concentration of the reactant at time T is equal to 0. A is the concentration of the reactant after some time T. So just remember, I repeat again, just remember, we can derive the rate constant for first order reaction. We can derive the rate constant for first order reaction. Let us consider the reaction. A gives product as a first order reaction. What's the meaning of first order reaction? Rate of the reaction is directly proportional to concentration of only one reactant. That is directly proportional to power of the concentration term 1. Such reaction is called first order reaction. So consider the general first order reaction. A gives product. At time T is equal to 0, concentration of the reactant A is A0. After some time T, the concentration of the reactant A is A. Now we know rate is equal to K into A power 1. You can rewrite minus dA by dt is equal to K into A power 1. You can rearrange this, concentrations are in one side. Minus dA by A is equal to K dt. You just integrate both the sides of the equation within the limits of A0 to A and T equal to 0 to T. So minus integration of A0 to A dA by A is equal to K into integration of T equal to 0 to T equal to T dt. On integrating, you will get this result minus ln A power A by A0 is equal to K T power T by T0. Now you substitute the limits. You know how to substitute? Upper limit minus lower limit. So you can write minus ln A minus of ln A0 is equal to K T minus 0. That is upper limit minus lower limit. Now you can rewrite minus into minus, this is plus. So ln A0 minus ln A is equal to KT. You know log A minus log B is equal to log A by B. Based on that, ln A0 by A is equal to KT. You can rewrite K is equal to 1 by T ln A0 by A. You can convert ln into log. So you know how to convert? Ln is equal to 2.303 into log to the base 10. So you can rewrite K is equal to 2.303 by T log of A0 by A. This equation is called rate constant for first order reaction. So you just practice once and twice, write and practice. Very important reaction, and the formula is very important. Based on that, you will have few problems. Okay. Now let us see the graphical representation of the first order reaction. We know that K is equal to 1 by T ln A0 by A. You rewrite KT is equal to ln A0 minus ln A, and you can rewrite ln A is equal to minus KT. Ln A is equal to minus KT plus ln A0. And this equation looks similar to y straight line equation, y is equal to minus mx plus c. Now you see, if you can plot the graph x y ln A in y axis, t in x axis. So if you plot the graph ln A versus t, you will get straight line with a negative slope. The slope of the straight line is minus k. The intercept of the straight line is ln A0. You just remember from the straight line equation, y is equal to minus mx plus c. If you plot the graph x versus y, you know what is that y? Ln A. Take ln A in y axis, t in x axis. If you plot the graph, you will get straight line with a negative slope. The slope of the graph is minus k. The intercept of the graph is ln A0, from which you can calculate the plot of ln A versus t gives a straight line with a negative slope. Slope is equal to minus k. The intercept is equal to ln A. This is graphical representation of the first order reaction. Just keep it in your mind. Then, what is half-life period? Remember, this is very important. You will have simple problem like a 1 mark or 2 mark problem based on this topic. What is half-life period? Time taken or time required for one half of the reactant to disintegrate or reactant to react to form a product. You remember what is half-life period? time required for reactant concentration to reach half of its initial value. It is denoted by the symbol T off. You remember what is half-life period? Time required for the reactant concentration to reach half of its initial value. So you remember first order reaction, that it is of T off value is constant, does not depend on initial concentration. Let us see how. So there is a possible question. Show that first order reaction is independent of the initial half-life period of first order reaction is independent of initial concentration. Know how it is? You can derive an equation. You see K is equal to 2.303 by T log of A0 by A. And now instead of T you can see substitute T of A is equal to A0 by T, half of the initial concentration. Time is taken as T of, concentration of the reactant at time T is taken as half of the initial concentration A0 by 2. If you substitute in this equation, K is equal to 2.303 by T of log of A0 by half. You know well, the denominator of denominator will goes to numerator, the A0 gets cancelled, log 2. And remember, K is equal to 2.303 into 0.3010 by T of, which is equal to 0.6932 by T of. So T of is equal to 0.6932 by K. This is our equation for half-life period of first order reaction. You look at this equation. In this equation, there is no concentration term. That is why you can say half-life period of first order reaction is independent of initial concentration. You remember? Just remember both this equation, because in problems, one of the value may get cancelled with these two data. So it's very easy to get the answer. So you remember T of is equal to 2.303 into 0.3010 by K or 0.6932 by K. You can remember both this formula, the previous step. Also you just remember so that you can solve the problem very easily. And look at this equation. In this equation, there is no concentration term at all. So you can say the half-life period of a first order reaction is independent of the initial concentration. Remember, there is a two possible question. One, show that half-life period of a first order reaction is independent of the initial concentration. Or they'll ask derive equation for half-life period of first order reaction. Another question, they will ask some problems based on this half-life period. And you remember examples of first order reaction, very important, a possible 2 mark question. Decomposition of nitrogen pentoxide is a first order reaction. Decomposition of sulfuryl chloride is a first order reaction. Decomposition of hydrogen peroxide in aqueous solution is a first order reaction. Isomerization of cyclopropane to propene is a first order reaction. And very important, all radioactive disintegration reactions are first order in nature. You remember, these are the examples of first order reaction. Decomposition of nitrogen pentoxide N2O5, decomposition of sulfuryl chloride SO2Cl2, decomposition of H2O2 in aqueous solution, isomerization of cyclopropane into propene, and all radioactive disintegration reactions are first order in nature. So you remember, in this topic, what are the possible questions? Derive equation for rate constant of first order reaction. Or show another question, show that half-life period of first order reaction is independent of initial concentration. And they'll ask some problems based on half-life period. Another one, give examples for first order reaction. So these are all very important topic in the first part. Another part, in the same way, let us derive rate constant for zero order reaction. You see, zero order. What is zero order reaction? You know very well what is order. Sum of the power of the concentration term involved in the experimentally determined rate equation is called order. You know very well what is order. Sum of the power of the concentration term involved in the experimentally determined rate equation is called order of the reaction. What about zero order reaction? The rate of the reaction does not depend on the concentration of the reactant. So the sum of the power of the concentration term is zero. The change in the concentration does not affect the rate of the reaction. So remember, the rate is independent of the concentration of the reactant is called a zero order reaction. Let us consider a general zero order reaction. A gives product, rate is equal to K into A power 0. Look at this term, K into rate is equal to K into A power 0. Whereas in first order reaction, what we discussed, rate is equal to K into A power. This is the only difference. Remember, power of the concentration term is 1, is a first order. Power of the concentration term is 0, it's a zero order reaction. Now let us you see, at time t is equal to 0, the concentration of the reactant is A0. After some time t, the concentration of the reactant left remaining is A. Now you substitute this value in this equation, minus, instead of rate you can write minus dA by dt is equal to K, and you can rewrite this, you can rewrite the dt, you can take it this side. So what you can say, minus dA is equal to K dt. Integrate this reaction, integrate this equation between the limits A0 at time t is equal to 0 to A at time t. So remember, now integrate this equation, minus integration of A0 to A dA is equal to K integration of 0 to t dt. If you integrate, you will get minus A power A by A0 is equal to K into T power 0 by T power T by 0. See, remember, substitute this upper limit and lower limit. Minus A power A by A0 is equal to K T power T by T0. So now you substitute the limits. How will you substitute? Upper limit minus lower limit. What is the upper limit here? A. So A, what is the upper limit? Actually you will get A minus of minus A0. Minus of minus A0 is plus. So that is why you will get the equation A0 minus A is equal to KT. Here you know how you will get T minus 0. That is T minus 0 is T. That is why KT. You rewrite K is equal to A0 minus A by T. This is the rate constant for zero order reaction. You remember, rate constant for zero order reaction is A0 minus A by T, where K is the rate constant of zero order reaction, T is the time taken, A is the initial concentration of the reactant, A0 is the initial concentration of the reactant, A is the concentration of the reactant after some time T. So you remember, what is the rate constant value for zero order reaction? K is equal to A0 minus A by T. As in the case of first order reaction, here also we will see graphical representation. You see, take this equation, K is equal to A0 minus A by T. You rewrite A, that is you bring this T this side, KT, then A is equal to minus KT plus A0. You rewrite this equation, A is equal to minus KT plus A0. Again, it looks like a equation for straight line. Y is equal to minus mx plus c. This looks like a straight line. Now you plot the graph, A versus T. A is taken in the y-axis, concentration of the reactant is taken in y-axis, time is taken in the x-axis. If you plot the graph, you will get straight line with a negative slope. Again, the slope is minus k and the intercept is A0. Look at the difference. So only the difference between zero order and first order, where we plotted ln A versus T. Here we plotted A versus T. You remember, in first order, ln concentration of reactant versus T. Whereas here we plotted just concentration of reactant versus time T. So remember, in first order reaction, the slope is minus k. Here also minus k. Where in the first, the intercept is minus ln A0. But here, ln A0, here it is simply A0. So remember, it's a very important. And then, same way we derive the equation for half-life period of zero order reaction. You remember, K is equal to A0 minus A by T. T is taken as T off. You know what is half-life period? What is half-life period? Time required for one half of the reactant to react. One half of the reactant, the concentration of the reactant to reach one half of the initial concentration. T is taken as T off, A is taken as A0 by 2. Concentration of the reactant after some time T is half of the initial concentration. That is why A0 by T. If you substitute in this equation, K is equal to A0 minus A0 by 2 by T off. This you can rewrite T of is equal to 2A naught minus A naught by 2K, and you can rewrite T of is equal to A naught by 2K. This shows that the half-life period of zero order reaction is directly proportional to initial concentration. That's a very important point. Half-life period of first order reaction is independent of initial concentration, but here half-life period of zero order reaction is directly proportional to initial concentration. You remember, half-life period of a first order reaction is independent of initial concentration, but here the half-life period of zero order reaction is directly proportional to initial concentration. Okay. Now you see examples of zero order reaction. The reaction, you know what is zero order reaction? The rate of the reaction does not depend on the concentration of the reactant. Whatever change in the concentration of the reactant, rate will not change. It depends on other factor. Example, you see photochemical reaction between H2 and I2. Hydrogen and iodine react to form Hi in presence of light. The rate does not depend on concentration of H2 or I2. It depends only on the intensity of light. So it's a zero order reaction. Decomposition of N2O on hot platinum surface is a zero order reaction. Iodination of acetone in acidic medium is a zero order reaction. So you remember, the examples of both zero order and first order are important. They may ask some 1 mark question. You remember, photochemical reaction between hydrogen and iodine is an example of zero order reaction. Decomposition of N2O on platinum surface is a zero order reaction. Iodination of acetone in acidic medium is a zero order reaction with respect to iodine. So important it is. So we discussed integrated rate equation of first order and zero order reaction, half-life period and of zero order and first order reaction, then examples of both zero order and first order. Let's see at the topic, you know what is that? Factors affecting the reaction rate. It's a very, very important. What are the factors affecting the rate of the reaction? You remember, first, nature and state of the reactant. Nature and state of the reactant, concentration of the reactant, surface area of the reactant, temperature of the reaction, presence of catalyst. So you just remember, they'll ask in 2 mark, only the heading is enough. What are the factors affecting the rate of the reaction? Nature and state of the reactant, concentration of the reactant, surface area of the reactant, temperature of the reaction, presence of catalyst. Okay. Let us see one by one. So important it is. If you look at this nature of the reactant, generally what is chemical reaction? What is chemical reaction? Breaking of old bond and forming of new bond is called chemical reaction. The breaking requires energy. Forming a bond releases energy. The energy difference will play an important role in chemical reaction. You see, chemical reaction involves breaking and forming of new bond. The net energy involved in the processes depends on the nature of the reactant. Hence, the rate of the reaction is different for different reaction. You just remember, what is chemical reaction? Breaking of old bond and forming of new bond is called chemical reaction. While breaking the bond, you need to supply energy. While forming the bond, energy will be released. The net energy depends upon the nature of reactant. Say for example, when oxidation of oxalate ion by using potassium permanganate is very slow compared to oxidation of ferrous ion using KMnO4. You remember, oxidation of oxalate ion with KMnO4 is very slow when compared to oxidation of ferrous ion using KMnO4. You know why? That depends upon the nature of the reactant. Say that is why you know the oxidation of oxalate ion is oxidation of oxalate ion by KMnO4 is carried out at around 60 to 70 degrees Celsius. You know, only at that temperature the rate of the reaction is moderate and you can oxidize. So that is why the rate of the reaction depends upon the nature of the reactant. Because reaction is nothing but breaking of old bond and forming of new bond. The net energy of the reaction depends upon the nature of the reactant. And state of the reactant. What is the meaning of state of the reactant? Physical state. Generally, reactants are in gaseous state. They react faster than liquid state than in solid state. You can give an example. Say, if you consider physical state, gas-phase reactions are faster compared to the reactions involving solids and liquid. For example, when sodium metal, you remember when sodium metal reacts with iodine vapor, it reacts faster when compared to sodium solid. Metal react with solid iodine. You know why? Solid reactant reacts slowly compared to gas. So remember, nature of the reactant and state of the reactant also play an important role. You remember, generally reactant in gaseous states or react more faster than solids and liquids. Then concentration of the reactant. You remember, concentration increases, rate of the reaction is also increases. You know why? Concentration of the reactant increases, more collision between the reactant molecule. The reactant molecules collide more frequently with each other, more collision, so they reach the transition state, they cross over the energy barrier, they form a product. So remember, more concentration, number of molecules per unit area will be more collision, more rate of the reaction. That is why generally higher concentration, greater the possibility of collision, hence the rate of the reaction is more. So concentration of the reactant increases, the rate of the reaction is more. Effect of surface area. You remember, when larger surface area, more contact between the reactant molecule, more collision, more rate of the reaction. How can you increase the surface area? When the reactants are provided in finely divided state, when the reactants are given in finely divided state, very powdered state, more surface area, more collision between the reactant molecule, more rate of the reaction. You can explain with simple example. You take calcium carbonate, limestone. Powdered calcium carbonate is treated with HCl and marble chip is treated with HCl. You remember, powdered calcium carbonate react faster than marble. The powdered calcium carbonate contain calcium carbonate, marble chip also contain calcium carbonate. When both are treated with HCl, the powdered calcium carbonate react faster. You know why? It is in powdered state. Powdered state, particle size are very small. Smaller the size, more surface area, more contact, more collision, more rate of the reaction. So that is why, see, remember, the surface area is also play an important role in determining the rate of the reaction. More surface area, more contact between the reactant molecule, more rate of the reaction. Then, effect of catalyst. You see, what is catalyst? The third substance which is present in small quantity increases the rate of the reaction or alters the rate of the reaction without taking part in chemical reaction. So you remember, what is catalyst? What is catalyst? Substance which is present in small quantity alters the rate of the reaction without taking part in a chemical reaction is called catalyst. How does the catalyst increases the rate of the reaction? Catalyst increases the rate of the reaction by lowering the energy of activation. So you remember, if you plot the graph potential energy versus reaction coordinates, what will happen? You know, the red color line shows that rate of the reaction in the absence of catalyst. The green one shows the rate of the reaction in the presence of catalyst. You see that what happened? When you add a catalyst, the energy of activation becomes less. So catalyst will increases the rate of the reaction by lowering the energy of activation. That means, you know, the catalyst will find an alternate route, another path to form a product where the energy of activation is less. So the rate of the reaction is here. Catalyst increases the rate of the reaction by lowering the energy of activation. Okay. Temperature. How does the temperature affect the rate of the reaction? You remember, generally temperature increases, what will happen? The kinetic energy, average kinetic energy, temperature increases, average kinetic energy of the reactant molecule increases, more collision between the reactant molecule, more rate of the reaction, more product formation. It has been observed that for every 10-degree rise of temperature, rate of the reaction is increases 2 or 3 times. So you remember, it's approximate value. So you remember, what is the effect of temperature? Temperature increases, average kinetic energy. Temperature increases, average kinetic energy of the reactant molecules are increases, more collision between the reactant molecule, more rate of the reaction, more product formation. It has been observed for every 10 degree raise of temperature, rate of the reactions increases by about 2 or 3 times. So remember, factors affecting the reaction rate. What are the factors affecting the reaction rate? You should remember, even they may ask in just 2 mark, nature and state of the reactant, concentration of the reactant, surface area of the reactant, temperature of the reaction, and presence of catalyst. These are the 5 factors affect the rate of the reaction: nature and state of the reactant, concentration of the reactant, surface area of the reactant, temperature of the reaction, and presence of catalyst. You understand? Then we'll discuss one more topic, what is called pseudo first order reaction. Pseudo first order reaction. What is pseudo first order reaction? Simple. Certain reaction follows higher order kinetics. The order of the reaction may be 2, 3, 4 or more than that. So what you can do, when the concentration of all the reactants are taken in very large excess, about 100 times excess, the rate depends only one reactant. That reaction is called pseudo first order reaction. You remember, in a higher order reaction or in second order reaction, you remember, in a second order reaction, concentration of one reactant is taken in very large excess, about 100 times, then the rate does not depend on that reactant, it depends on the another reactant. Such reactions are called pseudo first order reaction. You remember, a second order reaction can be altered to first order reaction by taking the one of the reactant concentration is in very large excess, about 100 times. Such reaction is called pseudo first order reaction. You remember, in a second order reaction, concentration of one reactant is taken very large excess, about 100 times, then the rate does not depend on that reactant, it depends only on the another reactant. Such reaction is called pseudo first order reaction. Say for example, hydrolysis of ester. When methyl acetate on hydrolysis by water in presence of mineral acid, you will get acetic acid and methanol. Here, the rate of the reaction is equal to K into concentration of ester and water. If the reaction is carried out with large excess of water, when the water is present in very large excess, there is for 1 mole of ester, we need only 1 mole of water. But the amount of water is taken very large excess. The change in the concentration of water is negligible. So the rate does not depend on concentration of water, it depends only on ester. So what you can do, you can rewrite this equation, say K into H2O can be written as K dash. Instead of K into H2O, you can substitute K dash. Rate is equal to K dash into concentration of ester. This K dash is called pseudo first order reaction. You remember, pseudo first order rate constant. In second order reaction, concentration of one reactant is taken in very large excess, about 100 times excess. The rate does not depend on that reactant, it depends only on another reactant. Such reaction is called pseudo first order reaction. Okay. So remember, it's a very important 2 mark students. What is pseudo first order reaction? In a second order reaction, concentration of one reactant is taken in very large excess, about 100 times. The rate does not depend on that reactant, depends on another reactant. It's called pseudo first order reaction. This is an example. Okay. Then one more simple topic, rate determining step. So you remember what is rate determining step? Simply it is called as RDS. RDS. Slowest step of a chemical reaction is called rate determining step. A chemical reaction can take place in more than one step. A chemical reaction may take place in more than one step. The slowest step of the reaction is called rate determining step of the reaction. Say for example, Consider the decomposition of hydrogen peroxide. H2O2 decomposed to form H2O and O2 in presence of I minus. This is the reaction. But the reaction takes place in two steps. You see, H2O2 plus I minus will get H2O plus OI minus. Second step, again another molecule of H2O reacts with OI minus, H2O plus I minus plus O2. So, if you add these reactions, what will happen? Overall, these intermediates gets cancelled, I minus gets cancelled, H2O, H2O2, 2H2O2 plus 2H2O gives O2. Here the reaction takes place in two steps, but only the step 1 is slowest step. So, that step is called rate determining step of the reaction. So, remember, a chemical reaction can take place in more than one step, The slowest step of the reaction, slowest step of a chemical reaction is called rate determining step. Shortly it is denoted as RDS, rate determining step. Slowest step of a chemical reaction is called rate determining step. So, remember students, what is rate determining step? A chemical reaction can take place in more than one step. The slowest step of a chemical reaction is called a rate determining step. Okay. Remember students, in this video we discussed 4 topics. First order reaction, integrated rate equation of first order reaction, graphical representation and half-life period example. In the same way, zero order, integrated rate equation of zero order reaction, half-life period, graphical representation example. So, we discussed about first order reaction, zero order reaction and then factors affecting the rate of the reaction. Then we discussed zero, that is pseudo first order reaction and rate determining step. So, these are all important part in the kinetics. So, remember, first order and zero order reactions are very important, especially the derivation and half-life period are very important, examples are very important. So, practice this derivation twice and thrice and write the examples twice and thrice, write and practice, very important. Right, we will see you in the next video. Till then, bye. Thank you.